Hello, this is Lynn Jones. I'm going to talk here about the survey strategy simulations, investigations, and experiments that we did to explore the survey strategy for the Rubin Observatory Legacy Survey of Space and Time, the LSST. This is a more detailed talk about many of the experiments that we did. This should be good background for people who are trying to dive in and analyze the different simulations. But there were a lot of different experiments that we did, so this is definitely a bigger talk. Let's go. So the baseline survey strategy has been around for a long time. It meets the basic LSST goals, but it misses other opportunities for science. The basic survey footprint is shown there. You have the wide, fast, deep, has 18,000 square degrees. We need more than 825 visits per pointing. And in general, we can cover this part of the sky with the other footprint coverage over 10 years with 2 visits every 3 to 4 days. But how can we do better? So we've gone through a process for this. We had a call for white papers in 2018. The white papers were submitted from across the community. It was a great response. Thank you very much. The Science Advisory Council read through these white papers and gave a response. They gave us some guidelines on what experiments and investigations we should do next. So the simulations you see here are in response to that SAC request. So the SAC questions, you can find their report at that short link there. The basics are, what should the cadence of visits within the wide, fast, deep look like? This includes both the visit exposure time, the intranight cadence, and the internight cadence throughout the season. How should the survey footprint be defined for the wide, fast, deep? And what is the impact of varying the footprint for the mini-surveys, the North Ecliptic Spur, South Celestial Pole, and Galactic Plane? Now it turns out that that's very intertwined with how you define the wide, fast, deep footprint. So in the end, we've sort of simulated these all together. And so we call this just survey footprint. How should the deep drilling fields be observed? This primarily comes down to what should their cadence look like. And then what is the impact and advantage of mini surveys? So these are mini surveys in terms of very short, small fractions of the overall time. They're the Twilight NEO mini survey, short exposures mini survey, and a mini survey taking visits at high air mass for DCR measurements. So this brings us to a brief overview of the families of simulations. The families of simulations we ran, there was quite a lot. Some of the families relate to similar kinds of questions about the survey strategy. So I've tried to color code those here according to the underlying question. Sometimes there's some overlap between families. So the U pairs family, in this light blue up at the top, gives us some information about general parameters for the survey strategy. This was a FBS 1.4 run, and it covers when to unload and load the U-band filter out of the camera and how much weight we should put on the U-band filter, so how many visits we should have in U-band. From that, we took some basic parameters and we've applied them for the rest of the simulations. So wide, fast, deep depth is a 1.5 release, and so are most of these unless they're otherwise noted. So in this, we took the baseline survey footprint and we scaled the fraction of time in the wide, fast, deep between 65 and 95%. This is a useful family for testing how your metric scales with number of visits in wide, fast, deep. The baseline family includes sort of a mixed set of runs. Some of them have to do with the visit exposure time. So we did a run with one visit that's 30-second long and a visit which was 2 15-second exposures. So basically looking at, do you do 2 snaps or 1 snap per visit? Both of these had pairs in mixed filters. We also did a run that was a 1 by 30-second visit where the pairs were in the same filter. So following along with the sort of white color there, This talks about what should the visit exposure time be. So we've in the baseline, there's 1 by 30 seconds, 2 by 15 seconds. U60 family has a simulation where we changed the U-band visit time to 60 seconds, but then took half as many visits. Variable exposure time, we just made the exposure times variable between 20 and 100 seconds. This gives you a test for consistent depth of individual visits. Next is how do we distribute visits within the night? So that's sort of this pink color. In the baseline run, there's the question of pairs in mixed filters or pairs in the same filter. Third ops family adds triplets at the end of each night, between 15 and 120 minutes of triplet visits. The next line is green. These are all families which deal with the survey footprint on the sky and how we distribute visits between different filters. In the footprint family, we have various baseline and big sky footprints. The big sky is this extended north-south wide fast deep footprint that moves area away from the galactic plane where there's high extinction and moves it further north and south where there's low dust extinction. And then we do various experiments for filling in that gap. The baseline is the standard wide fast deep plus the north ecliptic spur and galactic plane, but then we did experiments with filling in those regions at different levels. Bulges is a family that takes that big sky footprint for the wide fast deep and then adds different kinds of galactic bulge coverage. And filter dist, this family takes a baseline wide fast deep band of declination, so it's a very, very basic survey footprint, and then changes the filter distributions across that survey footprint. This is interesting in terms of just the footprint because it's a simulation that does not have the northern ecliptic spur, but it's also interesting because the different filter distributions can show tests of photo Z metrics, for example. With outrolled dust and the rolling FBO, we did simulations which are just testing how you observe sort of over the season beyond a night. Outrolled dust takes a big sky footprint and then adds the outscheduler north-south variation between visits in the north one night, visits in the south the second night. So it adds this in various styles. The rolling FBO is a 1.6 release. So this is rolling footprint. It's a new style of doing rolling cadence. It still uses 2, 3, or 6 declination bands to roll across the sky, but it does it in a smarter way. These families of simulations sort of explore more independent effects in a way. The DDF family looks at different cadences for the deep drilling fields. We used an AGN, a desk, and a daily cadence. The good seeing family adds a requirement for good seeing images in various bands. This is a pretty mild requirement, but it does add sort of an extra requirement on visits over time. The blue band are experiments with adding very short mini surveys. So Twilight NEO adds a Twilight NEO survey with varying frequency, so varying amounts of time required. The short exposure family adds short exposures all over the sky with varying numbers. And DCR adds high air mass visits, varying numbers of these, but they are kind of interesting because they don't impact the number of visits in the wide fast deep, but change how those visits are taken. The even filters family is from FBS 1.6. This changes how the filter in use is chosen, with the idea being to distribute visits in different filters more evenly throughout the month. And finally, spiders is a test experiment where we try to align the diffraction spikes with the CCD X and Y columns. This means it would be easier to do image subtraction, but it might have effects for relensing. So that was our very brief high-level overview. From here on out, I'm going to look in more depth at each of the individual families and talk about what each one did. You may want to skip ahead to the different families. I've added the timestamps in the caption on YouTube. So let's go back to our overview of what our different families are. They're color-coded by the kinds of questions they're asking. This first one is the U pairs. This kind of comes into general parameters. So with the U pairs family, we varied the U band filter load and unload time and the weight on the survey footprint, basically the number of visits in U band. Basically, if you change the filter at larger values of lunar illumination, basically lunar phase, that makes the U-band sky coverage less patchy around the sky because you have more opportunities to take U-band visits. And it also provides more opportunities for transient classification that require U-band visits. Instead of concentrating all of the visits very close to new moon, it gives you more time available to have that U-band visit. We looked at what the depth achieved in these U-band visits was, and if it changed when we changed the interval of when the U-band was available, and it doesn't. It just improves the sky coverage and it improves transient classification. From this, we decided that we would take the 40% illumination and pair U-band with G or R. That's driven by the transient classification requirements. And we used the normal weight because we didn't want to change the filter distribution based on this run. So the wide, fast, deep depth. In this family of simulations, we varied the amount of time spent on the wide, fast, deep. So we use the traditional baseline footprint. Less time in wide, fast, deep means more time on other mini surveys, as you can see on the left. More time in wide, fast, deep means less time on other mini surveys, as you can see on the right. The SRD metrics and many other metrics scale with the number of wide, fast, deep visits. However, if your metric is particularly sensitive to populations that require visits in other parts of the sky, not the wide, fast, deep, or not just the wide, fast, deep, then you can see more complicated behavior. So in particular, metrics for populations which are concentrated around the galactic plane tend to show an opposite trend. Our next group of families deals with the visit exposure time. So the baseline family of simulations includes 3 simulations. One where we did visits having 2 by 15-second exposures, 2 snaps. One where we did visits having 1 by 30-second exposure visits, single exposure per visit. Both of those had the pairs of visits in each night in different filters. We also did a run with 1 by 30-second visits having the pairs in the same filter. Now, 2 by 15-second, 2 snap visits have a higher overhead. Single snap visits can get 8% more visits over the lifetime of the survey because of the lower overhead. We can't definitively say we're going to use 1 by 30-second visits until the camera is on the sky and taking data, and the survey strategy optimization committee, if that's what they choose. However, because the single exposure visits are more efficient, that's what we've taken to be our default for the rest of the simulations. You can typically scale the results down and you would have the similar overall simulation if you had 2 by 15-second 2 snap visits. If you run with pairs in the same filter, you can have 4% more visits over the survey because of lower overhead from changing the filter. But you do lose color information for transients. Looking further into the visit exposure time, so the baseline family had the single snap and 2 snap visits. We have the U60 family. In the U60 family, we modified the U-band visit time to 60 seconds and left other visits primarily at 30 seconds, except for the associated GNR band pairs, that went with those U-band visits, and those were at 60 seconds as well. That let us keep the timing of the pair separation the same for the entire set. Because we are using longer exposure times in U-band, we reduce the number of U-band visits. So reducing the number of U-band visits is problematic for a transient discovery that requires U-band, because you don't have as many visits, so you have less likelihood of having a U-band visit to go with your transient event. The U-band co-added depth increases by 0.2 magnitudes when you go to longer exposures. The reason for that is that U-band is, at 30 seconds, is typically read noise limited rather than sky limited. So by going to longer exposures, we get into that sky dominated noise regime, and the overall scaling of the co-added depth is better. Looking at one more experiment that deals with visit exposure time, we have the variable exposure family. So this family also consists of a single experiment. Here we varied the individual visit exposure time from 20 seconds to 100 seconds instead of keeping a consistent 30-second visit. The idea being that by varying the exposure time, you can reach a more uniform individual image limiting magnitude. So when conditions are bad, you take longer exposures. When conditions are good, you take shorter exposures. On the left is the distribution of visit exposure times that we had from this run. You can see that the mean exposure time increased to 32.2 seconds. This is something you could tweak by changing the parameters in the survey configuration. When we went to 32.2 seconds, we ended up with fewer visits overall, although the total open shutter time is very similar to that in the baseline run. The width of the individual image depth distribution is much narrower, and the individual image depths are shallower in U and deeper in Z. This is again probably something you can configure by tweaking those survey configuration parameters. The co-added depth reflects this change, and this is a little bit more problematic because of the fact that the U-band is read noise limited. So if you end up with a lot of short exposures in U-band, then the co-added depth is going to go down more significantly than just the change in the exposure time. All right, so looking at the intra-night cadence, says the cadence of visits within a night. In the baseline run, we already had pairs in mixed filters versus pairs in the same filter. In the third OBS family, we experimented with adding triplets at the end of each night. So the idea here is that we reserve a certain amount of time at the end of the night, between 15 and 120 minutes, depending on the configuration, and go for triplet visits for already observed fields. So if you had a pair earlier in the night, you would try to get a triplet on some set of those fields. GRIZY were used for the triplet, and it was supposed to match one of the band passes used earlier in the night in the pair. So at the top, in those top two plots, you can see on the left the baseline simulation, and on the right the triplet for when we had 120 minutes of triplets at the end of the night. And you can see what these are showing are the hourglass plots, which tell you the night of the survey at the bottom, the hour within the night as you on the y-axis, and the color at each point in the plot tells you which filter was in use. The big white areas are places of downtime. So you can see the seasonal variation in the length of the night. The very bottom is the wiggly line, is the lunar illumination. And what you notice is that on the left, we have a band near morning twilight at the top, where the filter is pretty consistent, and then that's a much longer band in the one on the right. So in the one on the left, we're just finishing up the observations in pairs, and the one on the right we're adding triplets for already existing pairs and then keeping the filter the same. With triplets, less new area would be covered each night. But if we keep this to sort of 15 to 45 minutes, it has a pretty low impact on other metrics, but we do need metrics that would be sensitive to the benefits because we also don't see a lot of benefit. One reason for that might be that field overlaps already got a lot of triplets and quads and more. So you can see this in the plot on the bottom left. That's the baseline run, and it's the number of visits per point on the sky. It's just a histogram of these, the number of visits. So at each point in the sky, we make a histogram of the number of visits per night, and then we add up those histograms over the entire sky. And on the right, you see the same histogram, but I zoomed in so that I could look more closely at the area around the triplets visits. And you can see that adding a triplet does improve this, but you were still getting more quads of visits from field overlaps already. So triplets help, but they may not be doing quite what we think they were doing. Or it might be that triplets do help because they have a particular time cadence that those field overlaps are not probing. So we need metrics that would be more sensitive to these effects. Now, the three families of simulations that deal with the survey footprint. The footprint family is a fairly large family that has a lot of different variations on the survey footprint. Basically, you can boil these down into two main types of footprints though. One of them has the baseline wide, fast, deep, and then adds different variations like more coverage of the galactic plane, so that you can see two examples of this on the left. Those are baseline-ish. The second variation on this has a big sky, wide, fast, deep. Now, big sky, wide, fast, deep also has variations in itself, but the basic idea is pulling area away from the galactic plane and moving that area to the north and south so that they stay in regions that are lower dust extinction. So a big sky footprint that has the galactic plane region defined by the dust limit is that plot in the center. But you could also define it by just a galactic latitude cut, and that would be the one on the right bottom. Or you could say, let's use the traditional kind of galactic plane, but still extend things north and south, and that would be the one on the right top. So we call these big sky-ish. And again, there's different amounts of coverage for the rest of the sky included in these simulations. Generally, the footprint family itself doesn't have a lot of big sky plus galactic plane coverage. That comes in the bulges family. So the bulges family takes that big sky, wide, fast, deep background and adds various levels of coverage across the galactic plane and bulge. And here we actually consider the plane and bulge separately. These were in the guidelines from the SAC. It also helps because that means we can cover the bulge more deeply without having to also cover the entire rest of the plane. Some versions of the bulges in the survey footprint in the bulges family have additional cadence drivers to prioritize visits at a particular kind of cadence. And then some of them also vary the I-band coverage relative to the other filters. So the bulges family adds galactic plane coverage to the big sky footprint. And then finally, the filter dist family is a very simple footprint. It's just a band of declination around the sky. It basically doesn't include any northern ecliptic coverage. It doesn't include any southern celestial pole coverage. It's very good galactic plane coverage, but not necessarily good for things like solar system object discovery. This is interesting to consider together with the other footprints because of the fact that it is the only one that doesn't have any northern coverage. But it also is interesting just in itself because it varies the filter distribution across this footprint. So it keeps exactly the same footprint, very simple distribution, and then changes the filter distribution like you see in the table there. When you look at metrics within this family, you can see that redder filter distributions are preferable for solar system objects, and supernova and possibly other transients prefer bluer filter distribution. What we're missing here is a photo Z metric to help us understand what the filter distribution should look like for galaxies. All right, so now we get to how to schedule visits throughout a season, at least a limited set of families on this. So rolling cadence and the ALT scheduler. ALT rolled dust. The ALT scheduler uses a fixed raster of the sky where it alternates between the north and south on a nightly basis. So this output had some nice features for supernova discovery. We decided we should test this within the feature-based scheduler. There are multiple simulations in this family. They all use a similar footprint, so it's a big sky with some coverage of the plane and celestial pole. But and we also had rolling cadence versions where instead of just alternating north-south, we also added a two-band declination on top of that. So in that case, the sky was actually split up into 4 regions. 2 of those regions were sort of in focus in the rolling cadence idea at a time, but one was in the north and one was in the south. So the interesting thing about these runs is that when you alternate between the north and the south, you increase your cadence at the 2-day baseline, but at the cost of decreasing your cadence on the 1-day or odd days. So basically you get even days but not odd days. And you can see this in the center 2 plots. The one on the left is the gaps between, number of nights between successive visits for a field, for the baseline on the left, and for the out rolled dust version on the right. So you can see the curve becomes much more like even nights you get coverage, odd nights you don't, and with the baseline you get just sort of a more even fall off. The last family in this group is the rolling footprint family. So this family comes out of the FBS 1.6 release, and we did have a rolling cadence family in 1.5, but you should use this one instead because it does a better job of covering the sky while we're rolling. So the basic idea here is that you split the sky into 2, 3, or 6 declination bands, and then you add extra focus on this band during the appropriate portions of the survey lifetime. So in the first year and the last year, we cover the entire sky because we need that uniform coverage for proper motion measurements. But in the other years, you could split it up into saying, even years I will, if you had a 2-band rolling cadence, you could say even years I will do the north band, odd years I'll do the south band. And we do try to do varying levels of coverage of the rest of the sky. That helps for things like if you need a template for a TOO observation, and just there may be some benefit for long-term monitoring of variables or just other objects where you would want observations in off years, but just maybe not as many. So the idea being, if you compress your visits into certain time periods, you can get a more rapid cadence during that time period at the cost of having a less frequent cadence in your off period. We don't see a lot of dramatic impacts in the metrics we have, especially for the 2 or 3 band, but we probably need more metrics sensitive to the changing cadence. I kind of think that the 6 band is maybe a little bit more vulnerable to weather variations. And plus we do see some negative impacts to solar system discovery, for example, but the 2 and 3 bands compared to uniform, pretty interesting. Okay, on to our next set of families, the DDFs. In the DDF family, we experimented with different deep drilling field cadences. So we took the standard baseline background survey configuration and just changed the deep drilling fields. So they're still the same pointings, but now we did an AGN cadence from the AGN white paper, a desk cadence from the desk white paper, and a daily cadence that was sort of an attempt to get daily coverage of the deep drilling fields. Each deep drilling field received 1% of the total visits in the desk and daily runs. The AGN final depths are a little bit lower, and their cadence was a little bit um, lower, so the number of visits for the AGN simulation are a little bit less in the deep drilling fields. Basically what we see is when you hold the deep drilling fraction, the amount of time we spend on deep drilling fields, constant, the impact to non-deep drilling science is pretty consistent. So we need metrics that are sensitive to the deep drilling fields and their cadence specifically. One problem is that the AGN and desk cadences are different enough from each other that to combine them will require more than 1% of the total visits per deep drilling field. The next family is the good seeing family. In this family, we added good seeing images in every year, just a requirement for that. The requirement was pretty minor, just a better than 0.7 arcsecond seeing image acquired in every year. And in these simulations, we tested it with requiring this in different bands or different numbers of filters. In general, we were getting similar kinds of good seeing images even without this basis function. So it's a gentle perturbation that has a generally favorable result. On the left, you see plots of the seeing distribution in various years. So you can see in some years, like the one on the top right, that's year 7, there was really very little difference between the baseline acquired seeing distribution and the seeing distribution that we got with this simulation. In some of the years, like year 2, which is the bottom left, you can see that this cuts out some of the tail of the seeing distribution. And in other years, like year 6, there on the bottom right, it actually moved the peak a noticeable amount to the left. This effect should show up more strongly in weak lensing metrics that we don't currently have in math. So this is another area where we need more metrics. Looking at the mini-surveys. So first up, the Twilight NEO. The Twilight NEO mini-survey added an NEO-focused mini-survey during twilight. So this was when the sun was -12 to -19.5 degrees. It turns out there's a lot of talk about using the twilight time. We were always using twilight time for observing. So this simulation always started when the sun's altitude was -12. In this case, we're now using various fractions of that time for this NEO mini-survey. The idea here were that these were very short exposure, 1 second, high air mass visits toward the sun during evening and morning twilight. In this family of simulations, we run that mini-survey either every day, every other day, every third day, or every fourth day, depending on the parameters. And the names of these runs are Mod 1, Mod 2, Mod 3, Mod 4. The footprint for the NEO mini-survey over the entire sky, when it's done, can be seen in the top right plot. And a single night execution of this survey is on the top left. So on one night on the top left, we took those fields. Over the entire lifetime of the survey, we would take the fields that sort of sum up to the top right. If you look at the solar elongation of all the fields taken in the twilight survey, you get a distribution similar to the bottom right. And this is useful because there's a couple of things you notice here. First of all, some of the fields are taken at fairly high solar elongation. This means they're fairly far from the sun. Part of this is likely because they're executing on a consistent pace throughout the month. So sometimes the moon will be in the area of twilight. So to avoid that and still execute the survey, the Twilight NEO mini survey would have taken fields that were further from the sun and further from the moon. This is something that maybe a different configuration for the mini survey would help. What you do notice though is that we get fields which are very close to the sun. So the dotted orange line there is the solar elongation of Venus. So adding these Twilight NEO fields lets us look very close to the sun and interior to the orbit of Venus. So this would be basically one of our only chances to find objects like Vatiras, which are asteroids which orbit inside the orbit of Venus. These are pretty interesting objects. They're hard to discover from the ground, but ZTF has recently shown it's possible. However, the Twilight NEO mini survey does have an impact on the amount of time we're spending in wide fast deep because it's executing during twilight time, which we were previously using. So if you run the Twilight NEO mini survey every night, it has a noticeable impact on even just on the solar system object discovery completeness. So what you see on the bottom left is the completeness for solar system objects of different populations at different sizes. So the solid lines in that plot are showing you, for the bigger objects in each population, what is their completeness. And the dotted lines are the smaller objects. And what you note is that as we execute the Twilight NEO mini survey more often, the smaller objects are less complete, while the larger objects are more complete. And this kind of makes sense because the exposures are very short and they are driving time out of the normal baseline survey and into these short exposures. And so the short exposures are still good to discover the large objects, but they're not so great for discovering the smaller objects. And so to me, this distribution makes sense. On the other hand, when you're running this less frequently, like every fourth day, the impact is not as significant, but it would still give you that opportunity to discover objects interior to the orbit of the Earth. The next mini survey are the short exposures. In these, we add short exposures of 1 second or 5 seconds over the entire sky. The idea here being you could tie into other catalogs more directly. There might be very bright objects that we want to study. In these mini surveys, we take these short exposures either 2 times per year or 5 times per year. And you can see in the plot on the left, so this goes from 2 seconds 1 time a year, 2 seconds 5 times a year, 5 seconds 1 time a year, 5 seconds 5 times a year. But by the time so what this was plotting is the number of long exposures that you have over the wide fast deep and just in the survey in general, the green line. If you do this very frequently, then you are taking what a typical long exposure survey time, about up to 7%. If you do this with 2 second exposures 1 time a year, you're not taking so much of the survey time, you're only using 2%. So obviously that has an impact on metrics which depend on the number of exposures in the regular survey, long exposures. What we're missing is the metrics that are sensitive to the benefit of these short exposures. Next mini survey family is DCR. The idea here being to add higher mass visits that let you make better DCR measurements. So DCR is useful because it's a differential chromatic refraction. If you look at the effect of DCR, how much it deviates the position of a high redshift quasar, for example, you can actually determine the redshift of the quasar from how much that position has changed, because they have strong emission line spectra, and so the effect of DCR can be dramatic. Higher mass observations also let you determine the approximate SED of a source. It tells you if it's redder or greener, for example. And this can be useful for building templates for difference imaging. So in these simulations, we add 1 or 2 high air mass visits in various filters, UG, UGR, UGRI. And in the plot there on the left, this is the distribution of air mass for U-band visits. The black line is baseline, the red line is when you have 2 visits that in U-band per year. So you're driving high air mass U-band visits. This mini survey has a smaller impact than you might expect on our metrics because those high air mass visits are still useful for observations. They're just, you're getting slightly less depth. What we need here are additional metrics which would be more sensitive to those DCR gains and to see if this is required for difference image template generation. The next family is the even filters family. This is a FBS 1.6 release. Basically, this changes how the filter for visit is chosen. Currently, the scheduler uses a basis function which looks at the difference between the current M5 and the darkest sky M5 per band. And that pushes bluer filters towards new moon, redder filters towards full moon. And so you get an uneven filter distribution throughout the month. For some purposes, a more even cadence between filters throughout the month, even if you get a worse limiting magnitude, is desirable. So this family of simulations modify this basis function to ignore the in-band sky brightness for U-band or G-band, and then it uses some other bandpaths to make that choice. These simulations use 2 different styles of footprints, a baseline footprint and a footprint that's in the big sky family. From the metrics we have, we don't see a significant impact, but I would expect this to reduce the image depths in U and G. This should have some benefit for transients, and it should have some detriment for solar system objects. But we don't see a big change. So this brings us to our last family, the spiders. In the spiders family, we ran a simulation where we aligned X and Y in the CCD with the diffraction spikes we'd expect for stars that are caused by the spiders in the telescope. So this fixes the camera rotation angle so that the CCD and the spiders align. It turns out we maybe don't have a lot of variation in this angle in the baseline simulation, so there may not be a lot of contrast in this simulation. However, we need further weak lensing metrics that are really sensitive to these effects to evaluate the impact for sure. What you see on the left are some figures that show the uniformity of the distribution of the Rote sky pause. Those are the 2 left columns. Rote sky pause tells you the distribution of objects in the sky on the camera. And Rote tel pause, Rote tel is the rotation angle of the camera relative to the telescope. So the top row is the spider simulation, the bottom row is this baseline simulation. There's not a lot of difference, and so we probably need metrics which are more sensitive to this. So now I'm going to just zoom through those slides that show you all of the families together one more time. We have families that looked at general parameters for the simulations, families that looked at the visit exposure time, families which looked at the intra-night revisits, pairs and triplets, families which looked at the footprint of the survey on the sky and the filter distribution, families which looked at how to observe fields throughout the lifetime of the survey, so rolling cadence. The DDF family, families which looked at how to take visits, so good seeing and even filters, families which looked at the effect of adding mini surveys, very short, small mini surveys, the Twilight NEO, short exposures, and DCR, and the spiders family. And I will leave this with an encouragement to go to community.lsst.org. There's a survey strategy section, And this is a great place for further discussion or to post questions. It's also where the release notes for these outputs can be found, including download links and links to the standard math outputs. See you on Community.